Hi, this is Akshay Patel presenting my solution to homework assignment 1. Here I've created a GUI that presents a summary of all the metrics for each search. If you would like to compare two different search functions, you may do that. For instance, if you do best first with Manhattan and A star with modified Manhattan, you can view the states that the program has taken. It's actually pretty cool. So now if we look at the code, the backbone of the code is this node class function. This node class. It stores the state, the total cost, the path length, the move taken to the node, and the predecessor of the node. We don't store the successor. To create a solution, we actually get a goal node from our search function, and then we just traverse the predecessor node chain all the way to the root to get the solutions path. Now our successor function, we get the index of the 0 in the string, and then we convert that index to a 2D matrix index, and then we determine whether or not it's possible to move in a certain direction. So for instance, if we do move up, we swap the indexes in the matrix, the 0 and the state above and the tile above it, and then we check whether or not that state has been previously visited before to prevent repeat states in search. So we have three heuristic functions for intelligent search. We have hcount, which is the misplaced tile count, hdist, which is the Manhattan distance, and then this third one, hdistCost, is the one that I've created, which is a modified Manhattan distance, where it multiplies the value of the tile by the Manhattan distance of the tile. So our search functions are all structured very similarly. We initialize the metrics, clear the set of expanded states, and then we create the queue, or the priority queue depending on which search you're using, and then we have the main loop. So in the case of breadth first search, we use a first in first out queue. We start by appending the node to the queue, and then our main loop pops the item from the queue, checks whether or not that state has been previously visited. Due to how these search functions, how the children are generated, if expanded state has not been expanded before, there might be that state nodes of that state still in the queue later on. So we check this. This is a constant time operation, which prevents repeated states from being checked. So in the breadth first search, we check whether or not we've reached the goal. If we have not, then we create the children, the successors. We add nodes of those successor nodes into the queue. And next is depth first. Same structure, almost the same code as BFS, except this time we use a first and last out queue with stack. And we similarly search for the goal state. Once we reach it, we return the goal node. Next is uniform cost. Uniform cost differs from BFS and DFS in that instead of a queue, we use a heap object, which is the priority queue. So in the case of the heap, if we expand a node, that means we have reached that node using the shortest path possible. So therefore, the first time we get to the goal node, we expand the goal node, that means we've determined the optimal path to the goal. And then the queue is sorted in priority order by the total cost to reach that node. Same thing we do for best first, where we have the priority queue, except this time the priority queue is sorted by the value of the heuristic function. For A star search, we combine the two. In the priority queue, what gets stored is the current total cost, which is from uniform cost search, plus the value of the heuristic function, which in the case of if the goal is the next node, that means this heuristic function will be 0. So we have created these search functions all with a similar structure, and the differences are as listed.